Hello. In this video, we're going to look at how we can algebraically solve a three-variable linear system. Now, we connected when we were looking at two-variable linear systems, we connected the algebraic solutions with a graphical solution. So if I have an equation, a system of equations in x and y, I can represent those two equations in the coordinate plane, two-dimensional, and the intersection is going to be a solution. A similar situation exists in three dimensions. It's just harder to kind of connect it graphically. But each of these equations here, so I have three variable equations in x, y, and z. Each of these equations could be considered to represent a plane in three-dimensional space. And like with a system of two equations, the intersection of these two, of the three equations, the solution of this system does have a graphical interpretation. So in this case, if I can find a solution that is a single value of x, y, and z, then that means that these three planes meet in a single point. It's much more common to have three variable systems that don't have a solution, a single point solution, because it's much more common to have three planes that don't intersect in a single point than to have two lines that don't intersect in a single point. But assuming that there is a solution, I can find it very similarly to how I solved two variable systems. So I'm going to number these equations 1, 2, and 3 because the more equations I have, the more steps I'm going to have to do, the more important clear communication becomes. And I'm going to set about as a starting point, I'm going to try and eliminate y. The reason I'm going to try and eliminate y is because two of my equations have y with a coefficient of either 1 or -1. For a similar reason, I could be trying to eliminate z to start off with because in equation 1 and 3, I have a coefficient of 1 and -1. I could also eliminate x if I wanted to, although it requires a little more manipulation, but I'm choosing y. So my goal here is to eliminate y. Essentially, because I can only eliminate one variable at a time, what I'm going to try and do is create two new equations that have y eliminated by combining two of the three equations twice. So to start off with, I'm going to add equation 1 with equation 2. That's the easiest way to eliminate y right off the bat. When I add equation 1 plus equation 2, 4x plus 2x is 6x. Y plus -y disappears, the y cancels out. And z plus 2z is 3z. And this will then be equal to 5 plus 10, which is 15. So now I've created an equation that has two variables. In order to figure out what the value of those variables are, I need another equation with those same two variables, because this will now turn this system of three equations with three variables into a system of two equations with two variables, which we've already learned how to solve. So I need to either combine equation 1 with equation 3 or equation 2 with equation 3 so that I will eliminate y again. I am going to number this new equation equation 4 because I'm going to use it a little later. And to eliminate y again, I'm going to combine equation 1 with equation 3. And the way to do that is I'm going to multiply 2 times equation 1, which would give me a y coefficient of +2. And then I'm going to add that to equation 3, which has a y coefficient of -2. The +2 and the -2 will cancel. So to see what that would look like, 2 times equation 1 is 8x plus 2y plus 2z equals 10. So that's 2 times equation 1. And I want to add that to equation 3. So 8x plus x is 9x. 2y plus -2y is gone. That disappears, which was my goal. 2z plus -z is just z. And 10 plus 2 is 12. This is now equation 5. So what I've done is I've reduced this equation to a system of equations that is like systems I have already solved. So now I'm going to try and eliminate again. So what I'm going to do is I'm going to multiply equation 5 times -3. So -3 times equation 5. And I'm going to add that to equation 4. It doesn't have to be that way. I could actually simplify. Actually, you know what? That is what I'm going to do. Equation 4, I notice everything is divisible by 3, so I'm going to start by multiplying equation 4 by -1/3. So -1/3 times equation 4 is going to give me -2x minus z equals -5. And then to that, I'm going to add, so -1/3 times equation 4 is going to be added to equation 5. So -2x plus 9x is 7x. Z plus z cancels. -5 plus 12 is 7, which means x is equal to 1. Now I can go back and work my way through these equations to figure out what z and then finally y are. So to figure out what z is, I'm going to substitute this 1 into either equation 5 or 4 or my modified equation 4. I'm going to sub it into equation 5. So I have 9 times 1 plus z equals 12, which means that z has to equal 3. And then I'm going to go back to one of my original equations. I'll go back to equation 1. So in equation 1, 4 times 1, because that is the x value, plus y plus z, which is 3, equals 5, which means that y has to be equal to negative 2. This means that the solution to this system, the point where these three planes intersect, is the point 1, negative 2, 3 in three-dimensional space. Notice that the coordinates are in the order x, y, z. That is the standard order here. So my goal when solving these systems is to take my system of three variables with three equations, make two different combinations that allow me to eliminate the same variable to create two equations with two variables, and then solve that either using more eliminations or substitution. Sometimes my job is made a little easier because I will have an equation that already only has two variables. So this is a system of three equations with three variables, t, u, and v, even though any one of the equations only has two variables. So essentially, I'm already halfway to my system of two variables, two equations. So I'm going to consider equation 1 to be the standard. I have t minus u equals 1. Notice that this equation has no v, so what I would like to do is I would like to eliminate v from the other two equations. Well, the way to do this, there's a couple different ways, but the way I'm going to do it is I'm going to take equation 2 and I'm going to subtract equation 3. So t plus v is essentially what I have, t plus v, minus v minus u on the left-hand side, and then 2 minus 7 on the right-hand side. So this becomes t plus u equals negative 5. And I'm going to call this equation 4. I can now add equation 1 plus equation 4 to cancel u, or I could subtract them to cancel t. But if I add them together, t plus t is 2t, negative u plus u is gone, 0, and 1 plus negative 5 is negative 4. So t equals negative 2. So in cases where not all of my equations have all three variables, part of the work may be done for you. So work smart and don't just kind of blindly start combining things without thinking about what variable makes the most sense to eliminate. If t equals 2, I can then go to, let's say, equation 1, or negative 2, sorry, negative 2 minus u equals 1, which means that negative 3 equals u. And then finally, I go back to one of my equations that uses either t or u in order to calculate v. So I'm going to go to equation 2. Equation 2 tells me that t, which is negative 2, plus v equals 2, which means that v equals 4. And therefore, the solution to this system, I'm going to put these values in alphabetical order. So TUV is negative 2, negative 3, 4. That's pretty standard when we're not using the normal x, y, and z, is to use alphabetical order. So TUV, that is the equation here.